Hello, everyone. Welcome to day 10? I don't know. I'm losing count. Maybe I should look it up. What is my actual thing? 10? Yeah, day 10 of programming every day until I graduate college. Today I'm going to take a little break from lead code. I'm getting sick of it. And I've been very busy with my schedule, and I don't know, it's just very crazy day today as I wasn't even one of my professors didn't even show up. We don't even know who the professor is. So my school, I question. But the day goes on, and the grind doesn't stop. So where the hell do I look at my videos? So yeah, I think it's day 10, if I'm not mistaken. Of course, yeah, we did day 9 yesterday. I went ahead and studied the solution from yesterday. Very interesting. I watched the NeetCode's video. He claimed that it was a bit harder of a medium, but very good design pattern, or like use of heaps and stuff, which is pretty nice. Never used heap. I don't think I used a heap like that before, but regardless, today I'm gonna do slightly something different. In terms of the project, hopefully I can get a simple project maybe by the weekend. I don't know. It's getting really hard to balance a project during the school year. But I need to learn Haskell as per requirement for my assignment for school. I don't necessarily need to know it really well. I just, I want to be a little prepared. Because I've never learned I believe this is a functional language, right? Is Haskell a functional language? I believe that's correct. Yeah, functional. I've never learned that before. So I'm kind of excited for it, but I should learn it. So I probably should. I need to go through at least the first 8 chapters. Sure, I'll try the first 8 chapters for today as my programming. So let's just go through it. So, I don't know if there's programming per se. Let me check actually. There's some programming. I'm probably gonna try maybe copying like what it does here. Yeah. Maybe I wouldn't copy everything, but I don't know. I'm gonna do some tinkering with the language because I've never done this type of stuff before. So yeah. Well, let's get to the introduction. So it says, "Welcome to Learn Haskell for a Great Good." If you're reading this, chances you want to learn Haskell, we've come to the right place. But let's talk about this tutorial a bit first. I decided to write this because I want to solidify my knowledge of Haskell, and because I thought I could help people new to Haskell learn it from my perspective. There are quite a few tutorials on Haskell floating around there. When I was starting out in Haskell, I didn't learn from just one resource. The way I learned it was by reading several different tutorials and articles because it explained something in a different way than the other did. By going through several resources, I was able to put together the pieces and it just came falling into place. So this is an attempt at adding another useful resource for learning Haskell so you can have a bigger chance of finding one you like. This tutorial is aimed at people who have experience in imperative programming languages. C, C++, Java, Python. I have some experience in Python and C++. Not C, and I actually need to pick up C, which for that class as well. So, but I don't think that's too hard. But I learned C++ first, but I don't know. But having programmed in a functional language before, like Haskell or OCaml, yeah, I've never touched. This is perfect. Although I bet that even if you don't have any significant programming, some smart person such as yourself will be able to follow along and learn Haskell. Great. Hashtag Haskell on the free node network is a great place to ask questions if you're stuck. Nice. Yeah. I failed to learn Haskell approximately 2 times because before finally grasping it because it was all just too weird to me and I didn't get it. But once it clicked after getting over the initial hurdle, it was pretty much smooth sailing. I guess what I'm trying to say is Haskell is great, and if you're interested in programming, you should really learn even if it seems weird at first. Learning Haskell is it's much like learning to program for the first time. It's fun, it forces you to think differently, which brings us to the next one. What is Haskell? It's a purely functional language. It is imperative. Imperative languages, you get things done by giving the computer a sequence of tasks that executes them. While executing them, it can change state. For instance, you set variable to a to 5 and then do some stuff, then set it to something else. You have the control flow structures for doing some action several times. In purely functional language, you don't tell the computer what to do as such, but rather you tell it what stuff is. Oh wow, okay. The factorial of a number is the product of all the numbers from 1 to that number. The sum of a list of numbers is the first number plus the sum of all the other numbers and so on. You express that in forms of functions. So it's kind of like you're writing descriptions of what you want to code, right? Imperative looks more like instruction in a linear sense, but I don't know. This is kind of what I'm getting at. What are you, some kind of liar? Oh, misread. Expect that information. You also can't set a variable to something and then set it something else later. If you say that A is 5, you can't say it's something else later because you just said it was 5. What are you, some kind of liar? Okay. So in purely functional languages, a function has no side effects. The only thing a function can do is calculate something and return it as a result. Okay. At first, it seems kind of limiting but it actually has some very nice consequences. If a function is called twice with the same parameter, it is guaranteed the same result. That's called referential transparency, and not only does it allow the compiler to reason about the program's behavior, but it also allows you to easily deduce and even prove that a function is correct and then build more complex functions by gluing simple functions together. Okay. This sounds fun. I think it's really nice. Very different way of thinking of programming. I'm very excited for this class. This class seems really fun. So, Haskell is lazy. That means that unless specifically told otherwise, Haskell won't execute functions and calculate things until it's forced to show you a result. That goes with referential transparency. And it allows you to think of program as a series of transformations on data. It also allows cool things such as infinite data structures. Oh wow. So say you have an immutable list of numbers x, s, and a function double me, which multiplies every element by 2, then returns a new list. If you wanted to multiply a list by 8 in an imperative language, and did double, it would probably pass to the list, make list once, make a copy, then return it. Then it would pass to the list another time, 2 times, result, return it. In a lazy language, calling double me on a list without forcing it to show you the results ends up in the program. It's sort of telling me, yeah, I'll do it later. But once you want to see the result, the first double me tells the second one it wants the result now. The second one says that to the third one, and the third one reluctantly gives back a doubled one, which is a 2. The second one receives that and gives back to 4. Yeah. The first one sees that and tells you the first element is 8. So it only does one pass through the list, and only when you really need it. That way, if you want something from a lazy language, you can make some initial data and efficiently transfer and amend it so it resembles what you want at the end. Haskell is statically typed. Very nice. When you compile your program, the compiler knows which piece of code is a number, which is a string, and so on. That means that a lot of possible errors are caught at compile time. So, very nice. Oh, Boat, my kind of brand here. It is a compile language, which is really nice. If you try to add a number in a string, the compiler will whine at you. Haskell uses a very good type system that has a type inference. That means that you don't have to explicitly label every piece of your code with a type, because the type system can intelligently figure out a lot about it. If you say 5 plus 4, you don't have to tell that it is a number. It can figure it out by itself. Type inference can also allows your code to be more general. If your function that you make takes two parameters and adds them together, you don't explicitly state their type, the function will work on any two parameters that acts like numbers. Haskell is elegant and concise because it uses a lot of high-level concepts. Haskell programs are usually shorter than their imperative equivalents, and shorter programs are easier to maintain than longer ones and have less bugs. Haskell was made... Oh, Lord. Did I miss... I don't know what I clicked on. Oh, there's some really smart guys with PhDs. Yada, yada, yada. Okay. Alright. And a Haskell compiler. Okay. Well, maybe I should install some I maybe need to install the compiler. I don't know if I have the compiler. Okay, that's very interesting. Haskell compiler Arch download. I don't know if there's a Arch wiki for this. Alright, I think I need to sudo pacman, I think sudo pacman gac cabal install. I'm just doing cabal. I don't know what the difference between the two is, but let's install this, right? I gotta do both. Let's just install that. So it has the .hs extension. Alright, starting out. What do we got for us? Damn, this package is insane. What is taking so long? Well, that takes, guess my internet is slow or something. Let's get started. If you have sort of a horrible person who don't read introductions to things and you skipped it, you might want to read the last section. We need to follow this turret and how we're going to load functions. The first thing we're going to do is GH's interactive mode and call some functions to get the basic feel for Haskell. Okay. Type in GHCI. Well, I gotta wait for this damn compiler to install. But I will skip to the video when it finishes. I think I installed it. I'm not sure. There were some weird errors. I might have to look into that, but I think it's good to go for now. But let's just go to the interactive shell mode or something. So if we could do like 2 plus 5, right? We do like 10 plus. Yeah, we got a little calculator here. 49 times 10. You know, got some basic and arithmetic. Pretty self-explanatory. A little pitfall to watch here for negating numbers. I have a negative number. It's always best to surround it with parentheses. Wait, did you say yell at you by doing... So wait, what's wrong with doing negative numbers? So 5... What is it? 5 times negative 3? Interesting. So it wants this. Like that. Interesting. Okay. Boolean algebra is pretty straightforward. As you know, and means a Boolean and that. Testing for equality. Yep. Oh, this is the does not. Okay. This is in Python. Some division decrementer or something like that. Or something. What about 5 plus llama? It's not a number, so it doesn't know how to add it to 5. Even if it was, even if it wasn't, we try to do true equals 5, whereas plus only by the same type of a thing. You can't compare apples and oranges. We'll take a look at closer look at types later. No, you can do 5 plus 4.0 because 5 is sneaky and can't act like an integer or a floating point. Can't act like an integer, so 5 is the one that has to adopt. You may not know, but if we've been using functions all along. For instance, a function that takes two number and multiplies it. As you've seen, we call it sandwiching in between them. That is what we call an infix function. Most functions that are used with numbers are prefix functions. So let's take a look at them. Functions are usually prefixed, so from now on, we explicitly state that a function is a prefix form, we just assume it. In most imperative languages, are called by writing the function name and then writing it in its parameters in parentheses, usually separate by commas. In Haskell, functions are called by writing the same name and a space, then the parameters separated by a space. For a start, we'll try then calling them by the most boring functions in Haskell. The suck function, oh wow, interesting name, takes anything that has a defined successor and returns that successor. As you can see, we separate the function from the parameter with a space. Calling a function with several parameters is also simple. The function's min and max takes two things that can be put in order, like numbers. Min returns the lesser, and max returns the one that's greater for yourself. Function application. Well, let's try that. Let's do min 1 8 10. Oops. Max 8 10. Quit. How do I leave the thing? I think it was Control D, but the GHCI, right? HCI. Show bindings. Is there like the clear? Whatever. Well, we get that. So these 10, the successor of 9 is 10. 10 plus the max. Oh. Calling a function by putting a space after and then typing out the parameters has the highest precedence of all of them. What that means for is that these two statements are equivalent. By putting a space after it and then typing out the parameters. So this is, what is it, 10? And then we take the max of this, which is 5, and then 6 is 10 plus 6, then 16. Okay. We want to get the successor of the product of numbers 9 and 10. We couldn't write successor 9, 10 because that would get the successor of 9, which would be multiplied by 10. So we would have to write that to get 91 by, okay. So if a function takes two parameters, we can call it an infix function by surrounding it with backticks. The div function takes two integers and does integral division between them. So div 92. But when we call it like that, there may be some confusion as to which number is doing the division and which one is being divided. So we can call it as an infix function by doing 92 div 10, and it makes it clearer. Lots of people who come from imperative programming tend to stick with the notation that parentheses should denote function application. For example, in C, you use parentheses to call functions like foo, bar, and baz. Like we said here, spaces are used for function application in Haskell. So those functions in Haskell would be foo, bar 1, baz 3. Oh, wow. Okay, so if you see something like bar 3, doesn't mean the bar is called with bar and 3 as its parameter. It means that we call the first function bar with 3 as the parameter to get some number. Then we call bar again with that number. In C, that would be something like, okay, which is relatively the same, but slightly different. In the previous section, we got to a basic feel for functions. Now let's try making our own. Open up your favorite text editor and punch in this and multiplies by 2. let's do just the main.hs. Is that a so could we say double me x equals x plus x. Well, let's call it, yeah, let's baby dot haskell. What? That's a weird bug. Okay. But when defining function, there's a... Oh, wait. Did I do that right? Baby... Is that correct? Functions are defined in a similar way that are called. The function name is followed by parameters separated by spaces. But when defining functions, there is a assignment or equals, and after that we define what the function does. Save this as baby.h hs or something. Now navigate to where it's saved and run the GHC from there. Once inside, do the colon pipe the baby. Okay, so it's like Vim mode or something. GCI and then colon baby. Do we put without the extension? Okay, one component loader is interpreted, and then we use the function double me 10. Very interesting language. Okay, very nice. Because plus works on integers as well as floating point numbers that can be considered a number really, our functions works on any number. Let's make a function that takes two numbers and multiplies each by 2, then adds them together. Okay, that's how you define the double parameter. Okay, and then what does that function do? Simple. We could define it as x plus y plus testing out produces predictable results. Remember to append this function to... So do we can define another one again. So we say this is, what is this one called? Double us. And we take a y. And this is times, what is it? Square that. And then y times that, right? GHCI, load the baby file, and double us with 2 and 2. Nice. Okay. As expected, you can call your own functions from other functions that you made. With that in mind, we could redefine double like this. True. I'm gonna have a teamwork section here. Learn Haskell. And then we'll have the compile over here, gh. And then we'll have this here. So I can use the double me, right? Let's say, so delete to the end of the line, and we'll do double me x plus double me x or y, right? Let's do load the baby file, and let's do double us. Some big ass, oops. Very nice. Or as expected here. Two, yeah. Okay. Getting it. So you can use reuse functions. This is a very simple example of a common pattern you'll see throughout Haskell. Making basic functions that are obviously correct and combining them into more complex functions. This way, you can avoid repetition. What if some mathematician found out that 2 is actually D and you have to change your program? You could redefine double me. Since double U is called double me, it would automatically work in this strange new world where 2 is 3. Functions and hashes don't have to be in particular order, so it doesn't matter if you define double first and then double s. If you do it the other way around, or if you do it the other way. Now we're going to make a function that multiplies a number by 2 only if that number is smaller than or equal to 100, because numbers bigger than 100 are big as it is. Okay, conditionals. Probably familiar with if statements from other languages. The difference between Haskell's if statements and if statements in imperative languages is that the else part is mandatory in Haskell. If in imperative language, you can skip a couple of steps if the condition isn't satisfied. But in Haskell, every expression and function must return something. Oh, okay. We could have also written if a statement in one line, but I found this more readable. Another thing about the if statement in Haskell is that it is an expression. An expression basically is a piece of code that returns a value. 5 is an expression because it returns 5. 4 plus 8 is an expression because x plus y is an expression because it returns the sum of x and y. Because the else is mandatory and if statements always return something, that's why it's an expression. Okay. If you wanted to add 1 to every number that is produced in previous function, we could have written it in its body like this. Okay. If then, it's not kind of like a Lua-esque, Python-esque, like ternary operator. What is that tick symbol there? Had we omit the parentheses, it would have added 1 only if x wasn't greater than 100. Now note the tick at the end of the function. That obviously doesn't have any special meaning in Haskell. In Haskell syntax, it's a valid character used in a function's name. We usually use tick to denote a strict version of a function. Okay, the one that isn't lazy or slightly modified version of a function or a variable. Because tick is valid characters and functions, we can make a function like this. Oh wow, a tick in a function, in a variable. Interesting. There are noteworthy things here. The first thing in the function name, we didn't capitalize Conan's name. That's because function can't begin with uppercase letters. We see why in a little bit. The second thing is that functions doesn't take any parameters. This function doesn't take any parameters. When a function doesn't take any parameters, we usually say its definition or a name, because we can't change what names mean once we've defined them. When a function doesn't take any parameters, you usually say it's a definition or a name. So it's like a variable, a really tacky way to do variables or something. We usually say it's a definition because we can't change what names and functions mean once we define them. Conan and Brian and the string it's me can be used interchangeably. All right. So this is like some intro, like the feel of that. I'll do some more list stuff here. Much like shopping lists in the real world, lists in Haskell are very useful. It's the most used data structure and can be used in a multitude of different ways to model and solve a whole bunch of problems. Lists are so awesome. In this section, we'll look at a basic of list strings, which are lists, and list comprehensions. In lists are homogeneous data structures. Okay. So there's several elements of the same type. That means we can have a list of integers or a list of characters, but we can't have a list of a few integers and then a few characters. And now, a list. Oh wait, so it means it has to be the same type? Is that what it is? Right? That's like the opposite of Python, right? Homogeneous list. Okay. I noticed that pattern in a lot of like lower level languages or like compiler languages, which is interesting. I'm gonna notice if it's a restraint or constraint that's constraint, you know? We use the let keyword to define a name in GHCS. Maybe maybe this is more like a constant here because you're not defining anything here. But this is more return something. I don't know. It's kind of an interesting take on this, but whatever. So we use the let keyword, something like JavaScript, and doing a let equals 1 inside a GHC is equivalent of writing a equals y in a script and loading it. Got it. So let this here and lost numbers. And it returns that. As you can see, lists are denoted by square brackets and the values in the list are separated by commas. If we tried a list like that, Haskell will complain that the characters by which they are denoted as characters between single quotes are not numbers. Speaking of characters, strings are just lists of characters. Hello is syntactic sugar for hello. Okay, because strings are lists. We can use lists functions on them, which is really handy. Well, I actually want to test that. So if I say so like let, what am I doing? So like let x, like x equals 1. What is going on right now? To, and then a quote here. Oh, who did this? Is that? I don't remember doing that, but. And then should that can reload this? Oops. Am I missing something here? Maybe I should retry it. Load the baby thing. Oops. Is it the oh? Is that what? Or is it because of the quote? Is it that? Would this be valid? No, it's not. It's doing saying parser, possibly indentation or mismatched brackets. How could that be? Let's see. Very interesting situation that I have going on here. I don't know what's wrong with this. Why am I missing something? Common task is putting two lists together. That is done by the ++ operator. Haskell complains that the characters, by the way, denoted as a character between single quotes are not numbers. Speaking of characters, strings are a list of characters. Yeah. We use the let keyword to define them right in GHC1. Oh, wait, is the let? Oh, is let is only for the interactive shell thing. So if I could load this again, the baby, and pop the, what was the variable? The x variable. It will return back that thing. Okay. So the let isn't then. So let me try this then. Let's try, oh, I didn't load it. So load the baby again. And then, wow, very descriptive. Interesting. Seems like it's a function too. Like variables are like just functions or something. Okay. I'm doing a equals 1. Then loading it. Alright, gotcha. Common task in putting two lists together is done by the plus plus operator. Watch out when repeatedly using the plus plus on long strings. When you put two lists, even if you append a singleton to a list, for example, going to walk through the whole list, the left side of the plus. That's not a problem when dealing with lists that aren't too big, but putting something at the end of a list that's 50 million entries long is gonna take a while. However, putting something at the beginning of a list using the colon operator, also known as the cons operator, is instantaneous. Oh, wow. Notice how the colon takes a number and then a list of numbers, or a character in a list takes a number and a list of numbers, or a character and a list of characters, where the plus takes two lists. Even if you're adding an element to the end of a list with plus plus, you have to surround it with brackets so that it becomes a list. Okay. So 1, 2, 3 is actually just syntactic sugar for 1, 2, 3, and then you add the list. Note that, and all are different things. The first one is an empty list. The second one is a list that contains one empty list. The third one is a list that contains 3 empty lists. So if you want to get an element out of a list by index, use the exclamation point. That indices start at 0. Okay, so not index 1 like Lua. So what is that? So that would get us 3. Okay, fire. Let's actually try to do that. Should I load this? Well, let's just let's fix this and let's try to do 2, and that is correct. Very nice. Okay. Very cool. But if you try to get the 6th element, you get an error, so be careful. What does the error look like if I try to do, like, prelude, index too large? But if you try to get the 6th, list can also contain lists. They contain lists that contain lists that contain, This is probably very useful for like matrices and stuff. The list with a list can be different lengths, but they can't be different types. Just like you can have a list that have some characters and some numbers. but can't be different types. Just like you can have a list that has some characters and some lists, or some numbers, you can have a list that has some list of characters and some list of numbers. Lists can be compared if the stuff that they contain can be compared. Lists can be compared if the stuff they contain can be compared when using less than, equal, greater than, and greater than equal to compare lists. They're compared in lexicographical order. First, the heads are compared. If they equal, then this second ones are compared. True. Oh, what the? Okay, what does this mean? Lexicographical order. First, the heads are compared. If they are equal, then the second ones are compared, etc. So that's bigger than this because of the first one. This is true because of that. And then this is equal, so you move on to the next one. That, and then 2 compared to nothing is always greater. Okay. That's true, and if this is equal. What else could you do? So does that mean, for example, does this mean here a few things? Let's create another variable, right? What does this mean here? Am I saying the first ones are different, right? Right? So this would obviously right, this is obviously would be like what? X equals y, which is false. But we're comparing the first things, right? Right, it's just to prove that, right? If I put this again, this would be true now, right? Of course. And if I change this to, this would be true. Or is that compare? Huh. I thought it said it would you can't have a list that has some list of characters. Yep. Oh, I guess first the heads are compared. If they are equal, then the second elements are compared. Well, I said this should have been right. So I guess this is, they just compare the whole list. Whatever. Okay, whatever. Here's some basic functions that operate on list. Takes a list, return its head, which is the first. Okay. Tail. Okay. Oh. Chops the list head off. Very interesting. Last takes the last element and it returns it. Okay. Init returns everything except the last element. Very interesting. But what happens if you try to get rid of the head of an empty list? Empty list. Okay. So what is the head of X? Tail of Y. Tail of X. Okay. And init of Y. Init of Y is what? Except the tail? What? That is a very interesting exclusion. Oh my, it blows up in your face. If there's no monster, it doesn't have a head. When using head, tail, last, init, be careful not to use them on empty lists. This error cannot be caught at compile time, so it's always good practice to take precautions against accidentally telling haskell to give you some elements from an empty list. A length takes a list and returns its length. Obviously, very nice. Length of X should 3. Length of Y is 3 as well. Y, okay. Reverse. Checks if a list is empty. If it is, it returns true. Otherwise, it returns false. This function instead of X is, if you call it. Okay. Okay, so use the function. We use function of null of x. This is false because it's almost in there. Reverse a list, reverse y, and then what happens to y now? Oh, it doesn't mutate it. Interesting. So it just returns a new copy. That's something to very consider. Takes a number and a list. It extracts many elements from the beginning of the list. So it takes a number and a list. It extracts that many elements from the beginning of the list. So take 3. So 5, 4, 3. Take 1 is just 3. That is very useful functions here. Take how many elements? Let's take 3 or like 2 from y. So if I combine these two, like reverse takes in a list, which returns. So if I take 2 from y, oh wow. Could I like this? So I'm taking the 2 from elements from y, then reversing it. Okay. It's kind of hard to wrap my head around that sometimes with the spacing. If we try to take more elements than they are in the list, it returns the list. Oh, take 0. Ooh, take 0 from y, take a billion from y. Oh, it just returns the list. Okay. If we get an empty list, drop works similarly. It drops the number of elements from the beginning of a list. So it takes away these 3 and okay. Minimum takes a stuff of list that can be put in some kind of order and returns the biggest element. Okay. Product. Elm takes a thing and a list of things. Okay. Okay. Elm takes a thing and a list of things, and you tell it if that thing is an element of the list. It's usually called as an infix function because it's easier to read that way. Is 4 in here true? Is 10 here? No. Okay. It's kind of like in. Texas ranges. What if you wanted a list of numbers from 1 to 20? Sure, we could type all the numbers out, but that's not a solution for gentlemen who demand excellence from their programming languages. Instead, we use ranges. Ranges are a way of making lists that are arithmetic sequences of elements that can be enumerated. Numbers can be enumerated. 1, 2, 3, 4. Characters can be enumerated. The alphabet is an enumeration of characters from A to Z. Names can't be enumerated. What comes after jump? I don't know. To make a list of containing all the natural numbers from 1 to 20, you just write 1 through 20. This is the equivalent of writing 1 through 20, and there's no difference in between writing one or the other, except that writing out one enumeration sequence manually is stupid. Fire! Oh wow, this is a very clean syntax. And it prints all the number out. Very nice. Ranges are cool because hold on. There's it inclusive on both ends. Yep. Okay, ranges are cool because you can also specify a step. What if you wanted all even numbers from 1 through 20, or every third number from 1 through 20? How would you do that? Is this simply a matter of separating the first 2 elements with a comma and then specifying what the upper limit is? While pretty smart, ranges with stems aren't as smart as people expect them to be. You can't do 1, 2, 3, 4 and expect to get all powers of 2, because firstly, you can only specify one step. And secondly, some sequences that are arithmetic are ambiguous if you if given by only a few of their first terms. To make a list of all the 20 numbers from 20 to 1, you can't just do 20. You have to do 20, then 1. My guess is it does some kind of difference math, and then it use that difference as the incrementer or something. Watch out with using. I actually want to try that. This is very nice. So if I want to go from 20 to 1, what would happen? It would stop. But if I specify, hey, 20, and then if I do 18, then that, so it'll be decrementing by 2 now, right? Wow. Very nice. My advice is not to use them in list ranges, okay? You can use ranges to make infinite lists by not just specifying an upper limit. Later, we'll go into more detail on infinite lists. For now, let's examine how you would get first 24 multiples of 13. Sure, you could do 13, 26. Oh, what the hell? But there's a better way. Take 24 from... Because Haskell is lazy. It won't try to evaluate the infinite list immediately because it will never finish. It will to see what you want to get out of the infinite list. And here it sees you just want the first 24 elements and gladly obliges. Okay. A handful of functions that produce infinite lists. Cycle takes a list and cycle into an infinite list. If you try to display the result, it will go on forever, so you have to slice it off somewhere else. Take 10, cycle 1, 2, 3. And cycles it into an infinite list. Oh, I'm curious what happens here. Cycle takes a list. Oh, Lord. Okay, it's like a wild true over here. And you just take 10. Oh. Repeat an element and produces an infinite list of that element. Just like cycling a list with one element. Oh. It's like cycling a list with one element. Okay. Although it's simpler to use the replicate function, just use the replicate function if you want to some number of the same element in a list. Replicate 3, 10, 3 returns 10, 10, 10. Okay. So replicate does what this does. If you ever taken a course in mathematics, you probably run into set comprehension. They're normally used for building out specific sets of general sets, a basic comprehension of a set that contains the first 10 natural numbers. Yep. If you want to write that in Haskell, we would do something like take 10 from 2 to... what does that do? This is a weird syntax here. What is the spread operator? Oh. 2 to 4? What is that? Let me see what that does. 2 to 4? Is that to infinity? Oh. And you're only taking... So that's... the dot notation is some kind of spreading, like, infinite, like, up to here. But if you don't specify that, it would just go on forever. But if you take 10... Okay. Take 10 from 2 4. But what if we didn't want to double of the first 10 natural numbers, but some kind of more complex function applied to them? We'd use a list comprehension for that. List comprehension, very similar to set comprehensions, will stick to getting that first, getting the first 10 even numbers from a row. The list comprehension we use is x times 2. X is drawn from 1 through 10, and for every element in 1 through 10, we have a bound to x. We get the element only doubled. Here's what that comparison is action. So you take the element and double it. Okay. So we get the desired results. Now let's add a certain condition or a predicate to that comprehension. Predicates go after the binding parts and they're separated by a comma. Let's say we only want elements which doubled are greater than or equal to 12, right? There's the condition. Cool, it works. How about if we want all the numbers from 50 to 100? I should try this out too. So like we want all the numbers. So let's do x cubed, and that's what we applied from numbers x. Do I point this to x from 1 to I don't know, 10, and then we specify for only numbers if x is, we put an if statement or we just put an expression. Expression x is less than 10 or something, or yeah, that looks cool. Or if x cubed or x times 3 is, yeah, very nice. That's okay. That's so like we create the list and apply that is it's very complicated to read, but mod, is that another function? Mod x 2 mod 7, that would be to 2 backtick mod 7. Okay. Note that weeding out the list predicates a filtering. We took a list of numbers and we filtered them by the predicate. Now, for example, let's say we want a comparison that replaces each odd number greater than 10 with a bang. So, what do we say? Gotcha. X does not equal these. Several predicates. Not only can we have multiple predicates in a list of comprehension. Alright, that's cool. Tuples and... oh, we're almost done. Okay. I see. I got the gist of it. I'm starting to get the gist. Now I know. Not only can we have multiple predicates in a list comprehension, we can draw from several lists. When drawing from several lists, comprehensions produce all combinations of given lists and then join them by the output function we supply. A list produced by a comprehension that draws from two lists of 4 will have a length of 16, provided we don't filter them. If we have a list 2, 5, 10, 8, 10, 11, and we want to get the products of all the possible combinations between the... oh, wow. Here's what we would do. X times Y. Oh, wow. That's very sugary. Haskell has a lot of syntactic sugar. As expected, the length of the new list is 9. How the list comprehension that contains a list of adjectives and a list of nouns for epic clarity. Wow. So I guess this thing is like assignment, but like a loop. I know. Let's write our own version of length. We could call it length. Underscore means we don't care what we will withdraw from the list. So instead of writing a variable name that we'll never use, we just write this. This replaces every element of a list with 1 and then sums that up. This means that the resulting sum will be the length of our list. This is a reminder that strings are lists, so we can use list components to process and produce strings. Here's a function that takes every strings and removes everything else except the character. See in the ABC. Wow. This is really nice. Okay. You could write comprehensions across several lines. If you're not in the GHCI, it's better to split along list comprehension across multiple lines, especially if they're not nested. Or like there's several ways to store into a SQL. There are fundamental differences. A list of numbers is a list of numbers. That's its type, and it doesn't matter if there's only one number in it or an infinite number of amount of numbers. Tuples, however, are used when you know exactly how many values you want to combine, and its type depends on how many components it has and the types of the components. They're denoted with parentheses, and their components are separated by commas. Another key difference is that they don't have to be homogeneous. Unlike a list, a tuple can contain a combination of several types. Think about how we represent a two-dimensional vector in Haskell. One could be to use a list. That would kind of work. So what if we wanted to put a couple vectors in a list to represent a shape on a two-dimensional plane? We could do something like that. The problem with that method is that we could also do stuff like, which Haskell has no problem since it's a list of lists, which but it doesn't kind of make sense. But a tuple of size 2 called a pair is on type, which means that a list that can have a couple of pairs and then a triple and then triple. So let's use that instead of surrounding there. That's a very nice kind of type very, very strong type heaviness right there. If we try to make a shape like this, we'll get this error. Awesome. I think I'm pretty good. Tuples. I guess you could do the same kind of operations. Where kind of are we? Table of contents. Made it to chapter 3. We got lots to go. I think that's a good stopping point. Yeah. Maybe for tomorrow's work, I'll do 3 to 6, and then Saturday, Sunday, I'll maybe do these last ones. Try to get to level 8. Definitely bookmark this. Very good read. I'm enjoying the read, but I think that's enough for a lot of mostly reading. But I did code a little bit, but I am trying to learn Haskell, so this is kind of my, yeah. So, yep. Anyways, thanks for watching. I'll see you for tomorrow's video.